Give it a second.
And we're on. All right. Hello, everyone. Online viewers of the future, and the one person we have here in the lecture hall with us. We are the UNSW Mathematics Society, and we've got me, Rashid, we've got Juan, and we've got Cyril, who are going to be teaching you the first part of our discrete math workshop for this term. So, as always, this lecture will be available online later on the UNSW Mathematics Society YouTube channel to watch. And we'll get started right away. So before we actually start with the content, we've got a quick announcement about an upcoming MathSoc event, and it's the camp. As every society does, we've got our own society camp, and it's coming up in the first or second week of next term. It's going to be very fun. All your friends are coming, so you should come too, right? Some information that you might want to know. The general admission tickets are currently on sale, so there are still some left, and you have to buy them before Friday midnight if you want to go. Or you can pay extra for the $290 tickets later on. And the camp will be held the first week back of term 2. That's the 31st of May till the 2nd of June. That's over the weekend. And to find the tickets, you just go to the UNSW Mathematics Society Facebook page. You'll find us there. All right, so let's get started. For this particular stream, we're going to be focusing on the first 3 topics. So that's sets and functions, modular arithmetic, and proofs. So to start us off, let's go through some sets and functions. Now, some basic revision of the sort of stuff that we'd be dealing with when we're talking about sets. We've got the power set. The power set of a set X, denoted P of X, is the set of all subsets of X. So that's a bit of a mouthful, but essentially if we've got, say, a set with 2 elements, A and B, then the 4 different subsets that we can have that are inside that set are the empty set, the set that just contains A or just contains B, or A and B, which is the set itself, right? And the cardinality of a power set is equal to 2 to the power of the set X, the size of the set X. And this is pretty obvious when you think about it, because if you've got all the elements of the set X, right? If this is our X, and we've got however many elements here, right? To create a unique subset of this set X, we ask ourselves, is the first element going to be in the subset? And that gives us 2 options, yes or no, right? And then we ask the same question of the second one. That gives us 2 options, yes or no. And this process continues for all of the elements of X. And obviously that's 2 to the power of the number of elements in X. That makes the number of choices that we actually have to make. The number of choices that we have. And that's the number of distinct subsets. Right, so that's easy enough. Another thing that you might want to know is the Cartesian product of 2 sets. So it's denoted A times B, and it's the set of all ordered pairs AB, where A is in A and B is in B. All right, so we've got, as an example, these 2 sets. X has the elements A and B, and Y has the elements 1 and 2. Then the Cartesian product of these 2 sets has 4 elements, 4 ordered pairs, A1, A2, B1, B2, right? This makes sense since it's pretty simple operation. If you want to, you can visualize it as kind of like a grid. We've got the elements of X here, A and B, and we've got the elements of Y here, 1 and 2, and then each cell of this sort of table that we've made would be a unique element of the Cartesian product. So we've got, A1, B1, A2, B2. Now, it is important that they're ordered pairs. So if you have x times y in your Cartesian product, then the elements of x will precede the elements of y in the ordered pairs in that Cartesian product. And as is probably clear from the table that I've drawn, the cardinality of a Cartesian product, x times y, is equal to the size of x times the size of y, right? Because you're just counting up the amount of cells in this table that you've made, which would be exactly, size of x times size of y. All right, so let's get into some problems. Suppose that A is this very messy set that we have defined, and B is the numbers from 4 to 9. And we have to find the size of the power set of the set difference of B and A. Okay, so first we need to find that set difference that we're talking about, right? And an easy way to do this is to first just write out what elements are in those two sets that we're talking about. B is all those numbers from 4 to 9, and if we actually calculate what's happening in that set A, then we get that it has 3, 4, and 7. Those are its 3 elements, right? And now that we've written them out like this, it's much easier to actually perform the calculation. So it's a good idea whenever you have a messy, ugly-looking set like that to actually write it out by its elements. And then it might be much easier to understand what's going on. So we've got this B minus A, this set, and we need to find the size of its power set. So this is pretty easy. We already know how to find the size of a power set. It's 2 raised to the power of this of the original set. So we get that the size would be 2 to the power of that size, which is 2 to the 4, which is 16. Now, second part to this question. We need to find the set difference of the power sets of A and B. So, first, obviously, we need to find the number of subsets of A, the size of the power set of A. And it's pretty easy. You raise 2 to the power of the size of A, and you get 2 to the 3, that's 8 elements, 8 subsets in A. And we need to consider, right, how many subsets would actually be shared between the power set of A and the power set of B, right? So the intersection of those two sets is 4 and 7. Those are the elements they share in common. So the only subsets of B that are also subsets of A are these 4 sets. So the size of this difference is the size of P of A minus how many is shared between them, which is 4. And you get 2 to the 3 minus 4, and that's equal to 4. Easy peasy. All right, and for the last part of this problem, we need to find the size of the power set of the Cartesian product of these two sets. So we're kind of combining everything that we've had so far. So let's find this Cartesian product, A times B first, or rather its size. This is pretty easy, right? We know from before that the size of the Cartesian product is the product of the sizes of the two sets. And that's 3 times 6, that gives us 18. And following from that, should be pretty obvious that the size of the power set is 2 raised to that size. That's 2 to the 18. All right. So far, any questions? Chat? Anyone monitoring the chat? Gentlemen? Yeah, are they cussing? Are they swearing? No? Yeah. They're behaving themselves? Yes. All right. Moving on. Now, we've talked a little bit about these sets, right, and how to work with them. And really the fundamental operators on sets are these symbols. You should recognize them. You hopefully do. We've got the union. This one's the union. And that's basically combining the elements of two sets into one. This is the intersection, and that's taking the elements that are in both sets and putting them into one set. And the complement of a set X, I've got X here, is all the elements that are in our universal set, right? So that's the set containing all the elements we could possibly care about, right, in the context of our question, that are not in X. So basically, everything except the stuff in X. That's what the complement is, right? And these operations, they can be combined and to yield different results. The way you actually operate with these symbols, the way you form algebra with them, is using the laws of set algebra, right? And that is available, you know, online in the slides, in the 1081 slides, in case you've forgotten any of them. So if you want to see how we would go about this question, here we would apply first De Morgan's law, right? So we're looking at this particular part of the expression, right? We've got the union of A and B, but the complement of that. And De Morgan's law says that we can bring that complement inside and change that union to an intersection, all right? And then now when we're looking at this part, we can distribute that to yield this, right? That's A union complement of A, and all of that intersected with A union complement of B, right? And now, if we have a look at this part, A union complement of A, that's basically saying all the elements that are in A and also all the elements that are not in A, right? And obviously that just yields you everything. That's the universal set. Now we have, as you'll notice, universal set intersected with some expression here, some set that's in the brackets, right? And if you take things that are in the universal set and also in something else, you just get back that something else, because obviously the universal set contains everything. Now we can distribute again. We've got B intersected with some stuff in brackets, and that yields this, right? And here we have, if we look at this part, we're looking at all the elements that are in B and also not in B, and obviously that yields nothing. No elements satisfy that, and that's why we get the empty set here, right? And finally, we've got something plus all the elements in the empty set, which is obviously just gives us back our something, our A intersection B. And that's the full simplification of this complicated expression here. So you can see that as long as you can identify which law of set algebra to apply at every step, it just becomes kind of systematic. It's pretty easy to simplify these expressions. You just have to revise your laws, especially the non-obvious ones like De Morgan's law, right? And the distributive law. And you should be fine. It's very systematic, these types of questions. All right. Before I move on, any questions about the laws of set algebra? No? No? Okay. Okay. Now onto functions. Some basic revision of what we talk about in relation to functions. We've got injective functions, right? So there's multiple different ways to interpret what an injective function is. So all three of these conditions are actually equivalent, and I'll go through all of them because some of them might be more useful than others in certain cases. A function f from the set A to the set B is injective if and only if for any x1 and x2 in A, f of x1 equals f of x2 implies that x1 equals x2. All right, so that's kind of a mouthful, but what that means is that if you've got two elements and the function of those two elements is equal, so if their two outputs are equal, then the two elements that you actually put into the function must also be equal. So if the outputs are equal, then the inputs must be equal, right? That's exactly what it says. If the outputs equal, then the inputs equal. Another definition is that for each output B in B, so each output in B has at most one corresponding input in A, right? So it means that you can't have two distinct elements mapping to the same element in the output set, right? In the codomain. And finally, another definition is in the diagram of f. So if you recall, that's when you draw the function as kind of an arrow map from the elements in the domain to the elements in the codomain. Every element of the codomain, so every output has at most one incoming arrow. So the function would be this map from the input to the output, and if we have two inputs mapping to the same output, it is no longer injective, because obviously we have two separate inputs that are not equal that have this an equal output, which makes it not injective. All right, what about surjectivity? A function is surjective if and only if for any output, B in B, there exists some A in A that corresponds to that output, right? So every output has a corresponding input. There is no element in your codomain that cannot be mapped to from your domain. Another definition, each output B in B has at least one corresponding input in A. That's basically saying the same thing as what we said previously. Another definition, in the diagram of F, so that's the picture that we drew before, every element of the codomain has at least one incoming arrow, right? So every element in that second bubble would have to have some arrow pointing towards it. And lastly, the range of F, which can be written as range of F, is equal to the codomain B, right? So essentially that just means that the set of values that you get from running the input values through the function is equal to the codomain, right? So any element of the codomain has a corresponding input in the domain. All right, some other important facts, right? We covered the formal definition of a function in 108.1.2, and this basically defined any function from x to y as a subset of the Cartesian product x times y, right? So it's the Cartesian product that satisfies that for any x, there exists some y such that this ordered pair is in the Cartesian product. And if there are two ordered pairs in F with the same first value, then this second value must also be the same. So basically what that translates to is that this first part tells us that for any x in x, there's some output for x, right? That's comes from our definition of a function, right? The function should be defined for every element in its domain. So every x in x, that's our domain, has to have some corresponding output. And the second one says that one input cannot map to two different outputs, right? We've got our one input, and it cannot be that these two elements, y1 and y2, are different, because otherwise that would mean that our function maps x to both y1 and y2, which is not correct, right? So that is our formal definition of a function as a subset of the Cartesian product. Another useful concept, the image, okay? So this is basically a way to denote subsets of the codomain, right? Given a function f from x to y and a subset s of x, so a subset of the domain, then the image of s under f, which is written as f of s, f of the set s, is a set of all output values attained by mapping all the input values in s under f. So basically, as a kind of convoluted way of explaining it, of defining it, but if we have our domain x and a codomain y, and our set S is some subset of the codomain, right? Those elements in the domain will map to some set of elements in the codomain, right? So in this case, it will be 3. And that the set of the elements that they got mapped to is what we call the image of S under F, F of S, right? Easy enough. And we've got the opposite of that now, which is called the pre-image, right? So that's basically starting with the codomain and ending up with a set in the domain. It's defined such that given a function f from x to y and a set S, then the pre-image of S under F, written f raised to the -1 of S, is the set of all input values that map to the output values in S under F, right? I don't really have space for a picture here. Maybe I can squeeze one in. So this is our codomain. This is our domain. And S is just a set in the codomain. That would be S. And then the preimage of S under F is all the elements, all possible elements that map to somewhere in S under F. So it could actually have more elements than S does if those elements map to the same one, for instance, right? Share an output. There we go. Bit of a unclear image, but I hope that makes it clear. Oh, lovely. Okay. Lots of space for pictures. All right. We'll move on anyways. Now, onto a problem. So, we've got this function, a function from the integers to the integers, and it's defined as the floor of x minus 1 over 2. And we're trying to show that f is not injective. And obviously that means that we must show that it's not true that for all x1, x2 in z, if the function of x1 and the function of x2 are equal, then x1 and x2 are equal. That's the definition of injectivity, right? If that's not true, then we need to find some counterexample, some pair x1 and x2 in our input space such that their outputs are equal, but they are themselves not equal. So basically two elements that map to the same output. And if you think about it, this is not too hard to find. So our first element could be 1. F of 1 maps to 0, right? And 2 maps to 0 as well, right? So these are two elements that have the same output. Outputs are equal, but 1 does not equal 2, so these two input elements are not in fact equal. That breaks our condition for injectivity, and therefore f is not injective. All right, any questions anywhere? All good? Okay, lovely. All right, a new question. So here we've got a set that's defined as a function of the integer n, and we're being asked how many functions is there from S7 to S8. So a good thing to do first off is to write out our sets. What is S7? You can do the calculation yourself, but S7 is actually the integers from 31 to 201. Chat, feel free to correct me. And that means that the size of this set is 171 elements. And we can do the same for S8. Starts with 35, ... and it goes all the way up to 261. And that means the size of S8 is 227, if I recall correctly. Feel free to do the calculations at home in your own time. But really all we need is actually the size of these sets to find out how many functions there are from S7 to S8, right? So as I'm sure we all like to do, let's draw our bubbles for the codomain and domain. This is S7, S8. And we've got lots of elements here. We've got 171 of them actually. And lots of elements here. 227 of them actually. There we go. All right. And we're looking for any functions from S7 to S8. So let's start with the first element. This arbitrary first element in the set S7. What output value could it map to? Well, it has 227 possible outputs that it could map to. So that's 227 options that we have for the first element. And we ask the same of the second one, right? There are no restrictions. They can map to the same element. So there's 227 options for the second element as well. It can map to 227 different outputs here. So, you know, for instance, you could go like this. And the same goes for actually for all elements in this domain, right? This one could map to the same one, for instance, right? It doesn't really matter. But what we found out is that we're making this choice 171 times. And that means that we're multiplying 227 together 171 times. And that's our answer, right? That's how many functions there are from S7 to S8. And you can actually generalize this to any two sets, right? In general, there are size of y to the power of size of x functions from x to y, from the sets x to y. All right, moving on. Now, we've got a restriction for our functions. How many injective functions are there from S7 to S8? Let's think about this. So, domain, codomain. Of course, I think a lot of the people watching would be able to do this in their head, but sometimes it does help to draw a picture. S7 and S8. Now, injectivity, what does this mean? That means that each output has at most one corresponding input. Basically, that means no two inputs can have the same output, right? So if we start off trying to count up how many different functions we can create, we start off the same way, right? There are 227 different outputs that the first element of S7 could map to, right? So say, for instance, it mapped to this one. But now that we go on to the second one, it no longer has 227 choices, but 226, one less, because if f is injective, then this second element cannot map to the same element in the codomain as the first element did, right? These two cannot have the same output, so we only have 226 choices for the second element. And this goes on, the pattern continues. The third one would have 225 different choices for which particular output we pick. And this goes on until we've subtracted 170 times, right? So the number of injective functions is all of these numbers multiplied together, right? Most of you would recognize that as P of 227 choose 171, right? So we're choosing 171 elements from 227 elements, which is our codomain, but without repetition, okay? And in general, there are P of the size of y and the size of x injective functions from x to y, right? Obviously, all of this depends on x and y actually being finite sets. Otherwise, obviously, there would be an infinite number of functions that you could create between them. All right, and moving on, we've got a different restriction this time. How many surjective functions are there from S7 to S8? Any thoughts? Okay, let's think about it. Once again, bubble diagram, 171 possible inputs, 227 possible outputs. S7, S8, right? What is our condition, the condition for surjectivity? If something is surjective, that means each output has at least one input. So for every element in our codomain here, there has to be at least one input that maps to it, right? We have to have an arrow that's pointing to every point in this second bubble, right? Now, how do we go about counting how many ways there are of doing this? Don't know? Okay. So, if we think about it, right? Each input in this domain can only map to one output in the codomain, right? So this one maps to one, this one can map to a different one, map to a different one, map to a different one, right? So the total amount of arrows that we're actually going to have is going to be how many? The same as the number of inputs that we have, 171, right? If we have 171 arrows, then we can't possibly get to all of the points in the codomain, right? So that means that each output will not have at least one input. And the total number of these surjective functions is 0 because none exist, okay? And in general, right, a surjective function from x to y, right, must satisfy that the size of y is smaller than or equal to the size of x, right? Otherwise, we'll end up with something like we have here, right, where we don't actually have enough inputs in our domain to map to all the outputs in our codomain. All right, any questions about that so far? No? All right. We're going on to next topic now, which is inverse functions, all right? So something that you might need to know is the definition of a bijective function, right? This is pretty simple. A function is bijective if and only if it is both injective and surjective, all right? And this is important because a function, f from x to y, only has an inverse if it is bijective, right, on that space. And this is pretty easy to see, right? If our function was, for instance, not surjective, so if it went like this and there was a hole, we didn't reach that output, right? Then so this is, say this is y, right? Then for our inverse evaluated at y would not actually, our inverse evaluated at y would be undefined, right? We wouldn't know what to put for that, what output we should give when plugging y into our inverse function, right? So obviously if our function has an inverse, then it has to be surjective, right? And what about injectivity? So if our function was not injective, so if it went like something like this, right? Oh, I'll draw that better. If we went like this, and we've got multiple inputs mapping to the same output, then our inverse function evaluated at this value would have to return 3 different outputs, right? Which is actually breaks our definition for a function, right? Not possible. So if our function f has an inverse of x, it must satisfy both surjectivity and injectivity. Otherwise, it can't happen, right? So that should be easy enough. And finally, another theorem. Our function from y to x, g, is an inverse of f, which is from x to y, if and only if g compose f, so g of f, is the identity function on the set x, and f of g is the identity function on the set y. So what that basically means is that g of f of x always has to return x, right? If g is in fact the inverse of f. And likewise, f of g of some element y in y has to always return our original input, right? And that makes sense, because obviously applying a function followed by its inverse will do nothing. The inverse has to reverse what that function does. Okay, so here's a little starter problem to think about. So if we have that for some value c, f of c is equal to c, how do we show that f of c is equal to the inverse of f at c? So we can start with just writing out what we're given. We're given that f of c equals c. And it's a good idea just to get that inverse in our expression somewhere. So let's take the inverse function of both sides. Right? And obviously, f of minus 1 of f of c would just return the value c, right? They would cancel each other out. And on this side, we have the inverse of f evaluated at c. And that means that f of c is actually equal to the to inverse f of c at that point. And that's basically part A proven, right? Easy peasy, right? So, oh yeah? So which step are you looking at? Which line? Second line. So what we've started with is what we've actually been given in the question, right? We're given that f of c equals c. And we're asked to derive that consequently f of c is equal to inverse f of c, right? So we start with what we're given. And what we've done in this second line is just take inverse f of both sides. So I applied this function, f minus 1, to the left-hand side and the right-hand side, right? And obviously, inverse f of f would just, they would cancel each other out, right? So we would just get c, and on the right-hand side, we get inverse f of c. So what we get through these three lines is that our function is actually equal to the inverse of our function at that point, okay? Easy enough. And for the second part, we need to find a function that actually breaks this, right? Find a counterexample to disprove that if f of c is equal to inverse f of c, so if the function is equal to its inverse at some point, then f of c equals c. All right, so this is a bit more tricky. So a good idea when you're thinking about functions and their inverses to think about the graph, okay? So for this one, for part A, we knew that at this point C, the function actually equaled to its input value. So the point intersected with this line, right? Y equals x, right? Or however you want to label it. But this diagonal line. And as we know, to find the graph of the inverse of f, we reflect every point on that graph across that diagonal line, right? So the inverse of f would actually look a little bit like this, right? And if this point on our graph actually lies on the line across which we're reflecting, obviously it's going to line up with the corresponding point on the inverse function, right? The graph of the inverse function. And that's why we have this result that the function is equal to its inverse at that point, because of that process of reflection. But here, we're going in the reverse direction, right? Say, for instance, so here's our diagonal line. We have some point on our graph, right? On our graph of f of x. So say f of a equals b, okay? And what we can do is take the inverse of both sides. So inverse f of a equals inverse f of b. And we get that a equals the inverse f of b. So given this point on our graph of f of a, we know that there must be this reflected point on our graph of inverse f, right? So there must be some point here on the graph of the inverse. And if we want our two graphs to intersect, then we just need to place a point in that spot on our graph of f of x, right? Of the function. So if f of b also equals a, then we get this result that f of b is equal to the inverse f of b. Okay? So any function that actually has this property where it has 2 points, right, reflected across the line, will have this property, okay? That it intersects with its inverse in places other than this straight line, this diagonal line. So if you want a specific counterexample, you could provide the function negative x, okay? So in this case, the inverse of negative x is obviously itself, right? To take the to reverse taking the negative number, you take the negative of that, right? So the inverse of negative x is just negative x. And if we look at the intersections of these two graphs, they'd just be intersecting everywhere, right? Not just on that line. And that's why it serves as a good counterexample to this particular problem. So what's our solution? We were looking for a counterexample to disprove that f of c equals, that if f of c equals inverse f of c, then fc equals c. And the example that we found is negative x. So how do we structure our argument? We say, let f of x equal negative x, then the inverse of that function is also negative x, and if we have that, then we can just take some arbitrary point, say for instance f of 1 equals minus 1, and the inverse of 1 is also equal to minus 1, so f of 1 is equal to the to inverse f of 1, but f of 1 does not equal to 1, right? So that's our counterexample. And we've disproven this statement that if f of c is equal to the inverse f of c, then fc equals c. Any questions? Is anybody monitoring? No questions? Question from you? All right. So we've got this question that kind of combines all we've learned so far. All right. So we've got these two functions, f, which goes from the interval 1 to infinity to r, and g, which goes from the real numbers to the real numbers. All right. And we're trying to find the domain and codomain of the composition of them, g of f. All right. So g of f will obviously start with us taking the function f, and then taking g of that function. So our input space is actually this interval, and our output space is the output of g, which is the real numbers, right? One thing that we do have to check, though, is that this function that we've been given is actually defined, right? And the way we check that is that the codomain of f, our first function, is a subset of the domain of g. And that's true because obviously the real numbers are a subset of the real numbers. And we can say that since the codomain of f is a subset of the domain of g, g composed f is defined. It's a defined function. And so we can simply say that the domain of g of f is the domain of f, which is that interval, and the codomain of this composition is the codomain of g, which is the real numbers, right? All right, part B, we're asked to prove that g of f is the identity map on this interval, 1 to infinity, right? So basically, it's the identity function. It always returns its input. So let's evaluate g of f, right? G of f of x is g of the natural log of ex, which returns natural log of x plus 1, right? And that's all raised to the power of e minus 1, okay? That simplifies to e to the power of natural log of x, which just gives us x, which is the identity map. So that's our solution. G of f is the identity map. All right. And for the last part, we need to ask that we're asked if it is true that f is the inverse of g, right? And we do need to recall what we learned before, is that f is the inverse of g if and only if f composed g is the identity map, okay? And what we found in the previous part is that it's true. We have proven in B that g composed f is the identity map for all x on this interval on our domain. So for f to be the inverse of g, we also need f composed g to be the identity map too, right? Because it has to go both ways. They both have to be inverses of each other. And in order to show that, we need to look at the domains, right? What we do notice is that the range of g is from 0 to infinity, because obviously the exponential is always positive, which is not a subset of the domain of f, right? Because we've got that 0 element in there and all the elements between 0 and 1 that don't fit into this interval, into our input of f, right? So we could have some output to g, right, where f of that output is actually undefined. And what that means is that f of g is not actually a function. It is not defined, and f is not the inverse of g. It's not the correct function that satisfies those two properties. All right, and that is the end of the sets and functions part of the revision seminar. I'll pass it on to Juan, which will take you forward through modular arithmetic. Thank you, Juan.
Dude, the mic's crazy, dude. Mic's crazy. Alright. So integers, modular arithmetic, and relations. Oh, I'm not gonna laugh, I'm pretty nervous. Alright. So first things first, we'll go through FLT. So what does FLT stand for? FLT stands for, oh my god, Yeah, it stands for Fermat's law theorem. So Fermat's law theorem, it states that, as you can see on the screen, for any prime p, any integer a, such that p is not a divisor of a, or alternatively, for our purposes, whatchamacallit, we will this is equivalent to um, a is not congruent to 0 mod p. We get that a to the p minus 1 is congruent to 1 mod p. So another way you could write this, you might have seen it written like this. It's a to the p is congruent to a mod p. The reason you would write it like this is because then you wouldn't need this condition anymore. But that's just like more of a fun fact. But anyways, ooh, how do we scroll? Oh wait, okay. So how would we use Fermat's law theorem here? We note that 307 is prime, and by Fermat's law theorem, we get that 8 to the 306 is congruent to 1 mod 307, since 307 is prime, and this happens if a is not a multiple of 307. So we know that 303 is not a multiple of 307 because it's less than 307. So we thus conclude we can set our a to be equal to 303, and thus we get that 303 to the power 306 is 1 mod 307, or 303 to 306 mod 307 is congruent to 1. So that's just basically what Fermat's law theorem is. So, example of how you might use it, and the thing with Fermat's law theorem is that it doesn't have to you can use it. It doesn't have to perfectly align. So here's an example. Find 303, but instead of 306, the power is 3063. So from Fermat's law theorem, we still get this, which is a useful result because we do note that 303 to the 3063, this is equal to 303 to the 3060 times 303 cubed. So this is equal to 303 to 303 to 306 to the power of 10 times 303 cubed. Oh, it's a bit laggy. So, you can kind of see that since from Fermat's law theorem, whatchamacallit. So from Fermat's law theorem, we get this is congruent to 1 mod 307. We get that we only need to calculate 303 cubed mod 307. As you can see here, this is kind of what we did. 303 to 3063. We just split it, and we get this is 1 to the 10. Another thing we notice is that 303, this is equal to minus 4 plus 307. So 303 is congruent to minus 4 mod 307. And we can just compute this, and we get our answer of 243 as desired. So in summary, Fermat's law theorem, it basically helps us reduce higher powers in certain prime mods. It can also help you reduce it in non-prime mods, but that requires some finicky stuff. I don't think it'll be in the course. Yo, what did I do? Yo, wait. Okay. It's fine. So here's a different question. We'll explore a different concept. We'll look through Bazal's identity, Euclid's algorithm, reverse Euclid's algorithm, all that stuff. So the best way to really explore an idea is to do it via question. As you can see here, we'll look at 2021 T1 Q4. So Matthew is trying to solve a modular congruence. 36x is congruent to 100 mod 208. So the question basically asks, could we reduce our mod to something lower? Could we reduce our condition to a smaller mod? So what we could do is if this number, if our 36, our 100, and our 208, well, not really 100, but 36, 100, and 208, we know that if there is a if their GCD is not 1, we can divide by their GCD. So that's why we apply Euclidean algorithm to find this GCD. And you can kind of just see here, we use Euclidean algorithm. It's just, it's just some arithmetic, and we finally end up with, okay, that GCD of 36 and 208 is equal to 4. So what this means is we by definition, right, we get our 36x is equal to 100 mod 208, and this is equal to 1. So it means that our 36x is equal to 100 plus 208k for some integer k. We move our k to the other side, make y equals minus k, and since our GCD is 4, we know that we can divide by 4. And the thing about the since it's our GCD, we can't really divide anymore. So we know that this is like kind of the smallest mod we can obtain, right? So Bazal's identity, so if we have our, okay, what did I write? So Bazal's identity basically says that if the GCD of A and B is D, then there exist integers x and y such that ax plus by equals d. If you do math 1a, you might say that d is, okay, never mind, I forgot what I was gonna say. But like, all right, so why would Bazal's identity be useful? The main idea with Bazal's identity is to show that there will exist a solution for this. So it's basically, we note that if our A equals 1 A equals 9, our B is equal to 52. So with our A equals 9, B equals 52, we know that there exists x and y that are integers. Ooh. Alright, so we note that there exists x and y that are integers such that ax plus by is equal to 1, since 9 and 52 are coprime. Or we alternatively get 9x plus 52y is equal to 1. So what we could do is we then would multiply both sides by 25 to get that 9 times 25x plus 52 times 25y is equal to 25. So that's basically, Bazal's identity, what it does is shows us that there exists a solution for our equation here. So idea here is we did our Euclidean algorithm to get the GCD. So instead of just like redoing it for 52 and 9, we can instead divide it by 4, right? And what we can do now is something called the reverse Euclidean algorithm. So what that basically is we express these smaller numbers in terms of the bigger ones. So how we would do this is we'd move 7 to the other side. Wait, was it 7? No. Okay, so we move this 5 times 9 to the other side. We'd move this 1 times 7 to the other side, and so on and so on. So we get that 52 minus 9 times 5 is equal to 7. And note that our 7 is now expressed in terms of 52 and 9, which are bigger numbers, basically. And like at the very bottom, we have like 2 is equal to 2 is equal to, how do you put it? Wait, never mind. But like you can basically do this for all of them. So you can have 9 minus 7 is equal to 2. So you can express 2 in terms of 9 and 7, which are bigger numbers. So that's basically the whole idea of Euclidean algorithm. And by using this Euclidean algorithm, we'll express our R1 in terms of 7 and 2, and then R2 will express in terms of 7 and 9. And we're just like kind of keep on slowly going up and up until we go back and we get our 52 here and our 9 here. So from this, we note that 4 times 52 minus 23 times 9 is equal to 1. And what we can do now is we multiply both sides by 25. So by doing that, we'll get 100 times 52 minus 557 times 9 is equal to 25. And we thus know one of our solutions is our solution for our pair x and y with 9x plus 52y is equal to 25. We note that one of our solutions is going to be wait, where did my blank? One of our solutions is going to be minus 575 and 100. So basically, reverse Euclidean algorithm, besides identity, it shows us that these solutions exist, but the reverse Euclidean algorithm is how we will get the solutions. So does that make sense? Right. So from there, we note that our solution for our original question, which is basically 9x is congruent to, oh shoot. So 9x is congruent to 25 mod 52. We note that one of our solutions is going to be 49, just by reducing our minus 575 in mod 52. So, oh wait, wrong one. So now we look to write the solutions as a set of integers with respect to the original modulus. So to check if there are solutions and how many there are, there's this little lemma. It's checking solubility. So we consider ax plus by equals c for integers a, b, and c, and a and b are both non-zero. So the number of solutions for x and y is 0 if c is not a multiple of a and b, and it is the GCD of a and b if c is a multiple of the GCD of a and b. So in our example, we note that what this effectively is that, okay, I can zoom in, that's crazy. So what this effectively is that, oh my god, why did this select? Is that our 36 is our A, our 100 is our, wait, oh, this is so much better. Oh wait, so our 36 is our A, our 208 is our B, and our 100 is our C. We note that from before, the GCD of A and B was 4, and 100 is clearly a multiple of 4. So we note that there are solutions. Not only there are solutions, but we also note there are 4 solutions here. So how do we get our solutions? We get them by repeatedly adding m divided by d until we get all of our solutions. So in this case, since our d is 4, our mod m, our m here, is 208, we'll keep on adding 208 on 4 onto our original solution, which was x equals 49. So 208, it equals 52. So we just keep on adding 52. We add 52 here again, and we just add 52 to get our set of 4 solutions. So are there any questions? Do you want me to explain anything? Okay. So So that's basically kind of like how we look to solve things used with Euclidean algorithm. It's how we would solve equations in the form of AX is congruent to C mod B, or equivalently, AX plus BY is equal to C. So this is how to solve. So this is how to solve. Yikes. Okay, so here's another example. So given that 1367 is prime, and specifically that 67 squared is equal to 388 mod 1367, whatchamacallit, we're also given that, so, okay, we're given that, oh shoot. Okay, so we're given that this number here is a prime. We're given that 1367 is prime. We're also given this, like, this congruence in mod 1367. And we're given that x equals 67 plus 1367t. So now what we want to show is that x squared, so we're given that x squared is congruent to 388 mod 1367 squared if and only if AT is congruent to B mod 1367 for some A and B. So what we're trying to look for is we're trying to look for the A and B that makes this work. And okay, also okay, no, I'll just say it later. So okay, so if in doubt, like one thing you can always fall back on is your definition, right? It's just like how things are defined in your question. So we note that x equals 67 plus 1367t. So we just substitute that in. That's just something that you naturally do. And then next we'd expand this, and then we move 388 to the other side. So we get this 67 squared minus 388. The actual value specifically is 3 times 1367, and then we have 2 times 67 times 1367t plus 1367 squared t squared. This is congruent to 0 mod 1367. But we note that each of these terms, since this is 3 times 1367, like 1367, there's a 1367 here, there's a 1367 here. We can effectively kind of divide both sides by 1367, and then we get 3 plus 134t plus 1367t squared is congruent to 0 mod 1367. But note that this 1367 is just congruent to 0. So this is congruent to 0. So we can get rid of it, and we move our 3 to the other side. And we get 134t is congruent to minus 3 mod 1367 as desired. So thus our A, so since we have this and we want our A and B here, we note that our A is equal to 134 and our B is equal to minus 3. Or if you like positive numbers, you can make your B equal to 1364. Ooh, I'll write it somewhere else. Ooh, so B is minus 3 or 1364 if you don't like your negative numbers. So this is the answer for this, for this first part of this question. So I think it's just it's just good practice. Like before we look to solve this AT congruence to B mod 1367, just always check solubility. Like it might be obvious, but I think just generally it's good practice because sometimes you're bound to just forget, and it ends up that there will be no solutions. So here we'll just check are there solutions? Will there be solutions, right? First of all, we note that since what was our A? If we scroll back up, our A is equal to 134, right? So since our A is equal to 134, so A is equal to 134, and we just notice that these two are relatively prime. So since this is our A, 1367 is our B, since it's the mod, we note that the GCD is just going to be 1. And 1 obviously divides any integer. So like we note that there will be solutions, and since they're coprime, the GCD is 1, and there will be one solution here. Right. So how would we solve this? We already went through how you'd solve this. So it's just we perform the Euclidean algorithm, and then from there we do the reverse Euclidean algorithm. And from there you can see that since 1 is equal, so like I'm not gonna go through it again because I think you should be like it's just the same as last time. So oh wait, okay. So from there we use Euclidean algorithm, reverse Euclidean algorithm. We get 1 is equal to 5 times 1367 minus 51 times 134. And if we take this mod 1367, we get our minus 51 times 134 is congruent to 1 mod 1367. And since we want solutions which are congruent to minus 3, we multiply this by minus 3. So we get 134 times minus 3 times minus 51 is congruent to minus 3. And our value of x, which is this, it'll be 153. So, and we note that this will be our only solution in mod 1367 because from before, our GCD was 1, and thus there will be one solution. So that's our solution. We found our value of t, and now we can use that to find our value of x. It's just, we simply sub it in. This becomes 153. You just add it up. It's arithmetic. Trust me that this is correct. Like, yeah. So that's basically it. Do you have any questions? Okay. So now let's move on to the relations part. So first we'll go over what a relation is. So kind of what a relation is when we say that we'll do x. If we say x or y, which it's basically saying, oh, x and y are related in this sense. And they're saying that like x and y follow this specific rule. So that's basically what we're saying. So x or y means that x and y follow a specific rule. Yo, why did it? So note that this rule will, note that when we say x or y, the order matters. So I think I should specify that it is an ordered pair. So anyways, here are some named properties of relations. So you can kind of read it. I'll just go through it anyways. So we say a relation is reflexive if all elements relate to themselves, or x are x for all x in your set. It's symmetric if x relating to y implies that y relates to x for all x and y in your set A. So if you view it like kind of like a graph, kind of like a directed graph where, I'll move over here. So if you have your, here's your set A, right? And then you have your arrows, which means that if you have some x and y, and if you have an arrow, it means x relates to y. So what symmetric means is that all the arrows will be double-sided. So all of these arrows will be double-sided, will point both ways. So what anti-symmetric is, it's the opposite of symmetric. So its elements only relate both ways with themselves. So if x relates to y and y relates to x, then x is equal to y for all x is equal to a. So if we go back to our graph, what this effectively means is that we instead of having every arrow is double-sided, we have the only no arrows are double-sided. They only point one way. So anti-symmetric, it's yo. Okay, so I should probably write this down. So it's two-sided arrow. This is one-sided arrow only. So we say relation is transitive if when x relates to y and y relates to z, then x relates to z for all x, y, z in A. So what would this mean in terms of our directed graph here? So it would mean that if you have x pointing to y and y pointing to z, it would mean that x points to z. Probably should make it clear. So this dun 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 and this dun 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 and this is z. Yeah, so that's basically what it means to be transitive. And yeah, so and we have an equivalence relation if it's reflexive, symmetric, and transitive, and it's a partial order if it's reflexive, anti-symmetric, and transitive. So here's an example of where we'll use these definitions. So the relation squiggly line on the set of reals by x squiggly line y if and only if f of x equals f of y, where f of x equals to x cubed minus 36x minus 79. So our first part is to prove that it's an equivalence relation. So if we look here, we just have to prove it's reflexive, symmetric, and transitive. So let's go down and let's prove it. So clearly, we note that it's reflexive because f of x equals f of x for any x because it's the same function. So hence we get that x is equal to x for, x relates to x for all like x, and our relation is reflexive. To show it's symmetric, we note that if x relates to y, we get that f of x is equal to f of y, but that also means that f of y is equal to f of x because equal signs work both ways. So we get that y relates to x. And to show it's transitive, if x relates to y and y relates to z, then f of x equals y and f of y equals z. So f of x equals, if it helps, f of x equals z, it's pretty obvious, but if it helps, I'll just put f of x is equal to f of y, which is equal to f of z. And thus, x relates to z. And therefore, our relation is also transitive. And since it's all three, it is an equivalence relation by definition. So, any questions there? Okay. So now we'll move on to part B. So we look to find the equivalence class of 0 with respect to our relation. So what is an equivalence class? The equivalence class of an element, we denote it as square bracket x, with respect to an equivalence relation, is the set of elements in S which are equivalent to x under R. So it's basically saying it's the set, so we define our equivalence class as the set of elements of S such that x relates to S. X relates to S, squiggly line. It removed it, no. So it's just a set of elements of S where S relates to S. This should be lowercase. But I think you get the idea. Yeah. So we note that f of 0 is minus 79. So we're looking to find everything that relates to 0. We note that f of 0 is minus 79. So we're looking for all real x such that f of x equals minus 79. So we look to solve this. Cubic. We get x cubed equals minus 36x. X cubed minus 36x is equal to 0, and we can factorize it, and we get the other two possible x's in the equivalence class are plus and minus 6. So thus we get the equivalence class of 0 is the set minus 6, 0, and 6. Yeah. So any questions here or? Okay. Alright. So we have the relation, same stuff, but okay, so we'll go back. So so symmetric is that all elements are related both ways, right? So so if x relates to y relates to x, or you could, if you draw like your graph, it's a two-sided arrow only. There are only two-sided arrows. So anti-symmetric is the opposite. It's where elements only relate to both ways themselves, which means that like whatchamacallit, like related elements only relate like one way. Or you could say that like that if you draw like your directed graph, there will be only one-sided arrows. Does that help or? Okay. Wait, what's the delay on the stream? Yeah. Oh wait, should I give an example? No. What? Just go on. Okay. Okay. So I'll probably go on until like response or whatever. So anyways, so we have this part C. I have COVID. So does there exist an element x such that equivalence class of x has two elements? So note that we can kind of like graph this function on Cartesian plane. So we consider this x, we consider this f of x, and if we have like some sort of graph here, right? This isn't the most accurate, but like we'll just run with it. The main reason I draw this graph is to explain this idea, which is that if we select a point that is a turning point, right, its equivalence class is the set of basically all points in which we draw a horizontal line. Ooh, a different color. We'll do a different color. So if we draw a line here, it will be the set of points which this horizontal line passes through, right? So the idea of thinking about a turning point is that if we consider the horizontal line at a turning point, it will only intersect here once, and it will intersect the graph again at another point. So it will intersect at 2 points. So that is the idea of considering the turning point. So we consider the turning points of f, and we differentiate it to find the turning points. So we note that the diff of f of x is 3x squared minus 36, and this will be 0 when x is 36 on 3, or the square root of 12. So if we consider our point at the turning point, it will intersect at this hump once, this hump here once, and it will intersect again at the graph at another point. So that means the equivalence class of our value, x equals the square root of 12, it will only contain 2 elements. So that's basically like the whole idea of it. So, does everyone get it? Are there any questions? Okay. So now we'll move on to uh, another question, 2021 T3, Q4. So we consider the, we consider the partially ordered set 7, 19, 133. Okay, there's a comma missing here. Wait. 361, 437, 2527, 3059, and 8303. And our partial order is divisibility. So, okay, like first things first, I think it's not part of the question, but I think it would just be a good idea to show that this is a partial order. So, show this is a partial order. So we need to show it's reflexive, but we can show it's reflexive because we know that every integer divides every integer divides itself by definition. So every integer divides itself. Oh, shoot. Itself. To show it's anti-symmetric, if we have that x divides y, and we have that y divides x, we note that wait, how would we say it? Okay, for simplicity's sake, we'll just say that x, the absolute value of x is less or equal than the absolute value of y, since x divides y. But we note that, whatchamacallit? Oh, wait. Actually? Wait. Okay. Oh, okay, yeah, okay. So we define this over positive integers. So since we define it over positive integers, we get that x divides y. It means that x is less or equal to y. And since y divides x, we get that y is less or equal to x. And from this, we get that x is less or equal to y is less or equal to x, which implies that y equals x. And to show it is transitive, actually, okay, to show it's transitive, if x divides y, y divides z, I'm pretty sure it's just okay, am I fine just saying that since if x divides y, y divides z, can we see that x also divides z? Yeah, so we can kind of just eyeball it. Yep, this is transitive. So it satisfies all three of these. So I'll probably underline black. So it satisfies reflexivity, it's anti-symmetric, and it's transitive. So that means that it is a partial order. So we know divisibility is a partial order. So what are we doing? So we're just kind of finding maximal, minimal elements. We're just finding the properties of our post set. So find the maximal elements and whether or not there's a greatest element. So definition, what is a maximal element? So a maximal element means there's basically nothing that's greater than it. So an x is a maximal element if and only if. For all other elements, x not an s, we have that x is not x is not less than x. X is not less than s in a sense. So what would help us with this is if we draw a Hasse diagram, right? So do people know what that is, or do you should I explain it? Okay, so basically just a brief over on it's we'll put all our elements on like whatchamacallit. We'll just write down all our elements. So 7, 19, 133, 361, 437, 25, 27, 30, 59, 8303. So we draw lines if like we draw lines from lower to higher elements if it satisfies if there's like a partial if they're related by the partial order. So we note that 133 is a multiple of 7 or 9. We note that uh, uh, 361 and 437 are also multiples of 19, and we get that 133 and 361 are divisors of 25, 27. We get that 43 and 133, 437 and 133 are factors of 3059, and we get that 8303 is a multiple of 361 and 437. So this is our Hasse diagram here. So this will help us find maximal and minimal elements. So we note that all of these elements here, it's pointing up to something. Like since it's pointing up to something, it can't be a maximal element. And if we note any elements here, they're not pointing. There's nothing pointing up from them, so they are all maximal elements. So what are our maximal elements? We'll just write them down. So our maximal elements are 252, 25, 27, 30, 59, 8303 are all maximal elements. Okay, I will bring this with us. Oh shoot. And that's fine. So now there's like the question is kind of two parts. So it's find the maximal elements and whether or not there is a greatest element. So what a greatest element is, it basically says an x in S is a greatest element if and only if for all other elements we have that S is like less than x in a sense, or like S relates to S, but it's like less than it. So if we look back in our Hasse diagram, right, we note that whatchamacallit, none of our maximal elements, right? Wait, why can't I change it? All right, so we know that none of our maximal elements are greater than greater than another one in terms of like being a multiple of another one. So since, like, for example, 2527 is not a divisor of 3059, and like 3059 is not a divisor of 8303, and 8303 is not a divisor of 2527. So we note that none of these top ones are greatest elements. We also note that none of these are greatest elements since they're not even maximal elements. So we can confidently conclude that we have no greatest elements. No greatest elements. So for part B, we'll reuse our Hasse diagram. We'll just migrate it. Hopefully it works. Okay. Wait. Ooh. Wait. Wait, yo, what happened?
Maybe zoom out.
Zoom out. Oh. Oh, okay, that's better. All right. So Okay, so we'll use our hash diagram again because it's kind of like shows us all the characteristics of the set we need. So let's find the minimal elements. We can see that everything here, everything up here, it has like something is less than it in terms of like divisibility, right? It has divisors in the set, so they can't be minimal elements. But we know that 7 and 9, they have no divisors in the set. The only divisor they have is themselves. So we note that the minimal elements. So we note minimal elements. We'll put it here. Min elements. They will be 7 and 19. Right? And okay, so that's basically the question. So any questions with that? All right. So okay, we will struggle migrating this. What? God. So okay, so part C. So now instead of looking what's the greatest, what's the least, we'll look at what are the upper bounds of 19 and 7. So what an upper bound is, what a lower bound is. So an upper bound of some elements x and y is an element such that it's like greater than your x and it's greater than your y. It relates to it in that sense. And similarly for a lower bound, it's a lower bound if and only if your element is less than x and less than y and it relates to it in that sense. So by using the hash diagram, we can kind of trace up what's greater than 7 and 9. So we note that the first thing that we see is 133, and we note that everything that everything that's like it's a divisor of is also is also an upper bound of 7 and 19 because it's an upper bound of 133 and transitive and partial orders are transitive. But we know that for all these other elements, like this are elements here, here, and here. We note that they are not We note that they are not multiples of 7, so it can't be an upper bound of 7. So thus we have all the upper bounds. So our upper bounds is 133, 2,527, and 3,059. So those are all our upper bounds. Okay. And for part D, instead of looking for upper bounds, we're looking for lower bounds. So we know the definition of lower bound from before. Okay, let's get rid of all this. Okay, so we have this poset, and we have to find all the lower bounds of 2527 and 3059. So we want to find the lower bounds of these two. We note that 133 is our first lower bound because it relates to those two. And we know that since 133 is lower bound, we know that 7 and 9 are both lower bounds. However, we note that these three elements, they are not lower bounds. We can just kind of see that 361 is not a divisor of 3059. 4037 is not a divisor of 2527, and this 8303 is just not a divisor of either. So thus our only lower bounds in the poset are 7, 19, and 133. So here are all the lower bounds. So yeah, I think that's it for relations, and I'll hand it over to Cyril. Okay.
Hello. We are going to be talking about logic and proofs. And as Juan wisely said, the best way to learn is by looking at some questions. So we've got this question here. we've got a set of arguments about people either passing or failing. I assume some kind of test or whatever. So here we have an either or a but not condition. The second condition here is a if condition, so like an implication. The third condition we have is an or, and the fourth one is a certainty condition. And so from all of this information, we have to certainly determine who will pass and who will fail, and who we don't know about. So a good way to start this question is to start from what we know for certain. So, as one might observe, we know for certain that Xavier will pass. Okay, so we know Xavier will pass. We see that right over here. Now, if Xavier passes, okay, let's have a look at that because we've marked that off. We're going to try and deduce if anybody else will pass or fail from that piece of information. We can see from 1 over here that either Warwick or Xavier will pass, but not both. That means both of them can't be passing, but at the same time, both of them can't be failing. So if you're familiar with XOR, which is exclusive, or one or the other but not both, we know Warwick must fail. Okay, so we finished with 1. So we know something about Warwick, and we know something about Xavier. So we're going to look for those two people in the other statements. And would you look at that? We know this and this. And now we want to look at statement 3. We can see that either Xavier will fail or Yusuf will fail. This is to say it's impossible for both of them to succeed. So we know Xavier definitely passes, so Yusuf must fail. All right, so we know that Warwick, Xavier, and Yusuf, we know whether or not they pass or fail. We know Xavier passes, Warwick passes, and, we know Xavier passes, Warwick fails, and Yusuf fails. But we don't know anything about Zoe yet. And the only information, the only statement where we know something about Zoe is statement 2 over here. So with that, we see that Zoe will pass if Yusuf passes. So we know Yusuf didn't pass. And this is an issue because this implication doesn't say anything about whether or not Zoe will pass. An implication is only false if we have something like true going to false. So we know here Yusuf doesn't pass, so we have false going to something. This implication here will always be true, whatever the result of Zoe passing or failing will be. So we can't determine anything new about Zoe, and thus we say that we're done with the question, because Zoe is not in any of the other statements, and there is no other piece of information that indicates what Zoe's grades are. Cool, makes sense? Nice. All right, let's look at a truth table for this equation. It's a logical proposition. So we want to know if it's a tautology, contradiction, or a contingency. So let's first deconstruct what all of that means. A tautology means that it's always true. If P, Q are true or false, or any combination of those, it's always true. This whole thing is true. Contradiction means it's always false. And a contingency means it can be either true or false. So there are some cases when the proposition is true, some cases where it's false. Let's look at that truth table. So you can see that to draw up this truth table, we looked at each of the cases for P and Q, right? So true, 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 false, false, true, false, false. But we also looked at their constituent parts. So we looked at the truthness or falsity of this and the truthness or falsity of this. And we've marked it down in these two columns here. And then we chained them up together, recalling that true to false is the only time this entire implication is false. And we can see that there is no true to false appearing in any of our table. Nothing there, nothing there, nothing there, nothing there. So this condition is always true, and thus it must be a tautology. And I have something for you logic, for you intuition enjoys. which is that we can deconstruct this semantically. Don't do this in an exam because they actually ask you to construct the truth table. But you can see, if you look at what this is saying if P and Q is true, right, then Q implies P. If you look at that, it means if P and Q occur, right, then when Q occurs, which always happens, then P occurs, which always happens. That's always true. They're both happening when they both happen, of course. Nice. Any questions? Cool. And then we will look at this question. Similar to the truth table question from before, we want to create a truth table. Well, we don't want to. We suppose there is a truth table for these propositions, and we want to know in how many of the 2 to the n lines this is true. So where 2 to the n comes from is, if you imagine a table, yeah, sure, let's go like this. If you imagine a table with like P1 to Pn, right? You can imagine there's some combinations of true and false. So say we start off with false, false, and false, and then we might go true, false, false. For each of the columns, there are 2 choices. So it can either be true and false, and so the total number of rows in the table will be a product of a bunch of 2's, specifically n 2's. So this is where the 2 to the n comes from. There's 2 to the n lines because there are 2 to the n choices of true or false for n stuff. Okay, now we want to know for how many of these this is true. Recall, again, for the 3rd time I'm saying, the only time an implication is false is when you have true going to false. And so we're going to actually take the negation of the statement, and we're going to find all the times, we're going to find the number of times it's false. So you can see here, this is when the statement is false, and the remaining n minus 2 propositions, where this is true and this is false, result in 2 to the n minus 2 choices. So we have 2 to the n minus 2 choices, where this thing here is false, and that must mean the other cases are true. So we simply take 2 to the n, all cases, minus 2 to the n minus 2, all false cases. And if we do some maths, grouping up terms, taking a 4 out, we get this number. And those are the number of lines when this guy here is true. Cool. Makes sense. Nice. Very cool. Also, YouTube live chat, feel free to ask stuff if I'm going too fast or anything. Sick. All right. We're going to move a bit away from the logic stuff, and we're going to look at proofs. So we have a function. So remember, and this is a, let's see, this is a bijective function. So a bijective function is one that's both injective, and surjective. And remember the definitions of what those mean. It turns out we'll only need injectivity. We'll see that. And we define f to the k as k compositions of this function. We're also going to define f to the 0 as the identity. So that means that an element, so f to the 0 of any element a is simply equal to a. That's what identity means. And we want to show that for each element a of a, there exists some positive integer k greater than or equal to 0, such that f to the k a equals a. Okay, so there's two things we want to do for this question, which are very important. The first is to try and use every important piece of the question. There's 2 important pieces. There's a bijective function, and there's one slightly subtle more piece of information, which is that a is a finite set. The second piece we want to use is that diagrams are very helpful. So we're going to try and look at what the set A looks like under a mapping of F. So let's say I have some elements in A. I'm going to represent them as dots. Okay? So imagine I'm drawing some lines over. So this line here means that we have a mapping here, that this element of A under F goes here. So this is A, and this is F of A. And note that F goes from A to A. Okay, so we're going to draw a line to represent a mapping. Now I'm going to keep on drawing some lines, right? And maybe I have a line going there. and I'm going to observe that A is a finite set. And what that means is that it actually must cycle back on itself. So let's say I go here, and let's say the cycle goes something like this. Notice something very wrong has occurred. It's not obvious right away, but it seems like this obeys our definition of a function. Maybe I have like a mapping here, and then it's like a two-way mapping, something like that. Sorry, this is very messy. But essentially, I have a cycle over here. Something very wrong has occurred, and it's that this element and this element map both to the same thing. And the issue with this is that this sort of goes against f being a bijective function. Specifically, f is injective. We can't have f of a equal to f of b and a not equal to b. Cool. So we've diagrammatically proved this question, but you might want to do this a bit more rigorously. In this manner, it's a bit tricky to prove rigorously because you have to consider the case that if you have a cycle and you're like comparing the previous element, right? These two elements could actually be the same. So you have to do some finicky stuff. We're going to use a similar argument though. Let's try and replicate each thing. So first, we're going to take a set. So first we define it's finite. And then we're going to take let's go with that. We first note that it's finite. And we want to somehow say that it cycles back because it's finite. And the most useful property here is the pigeonhole principle, which says that we can eventually double up. So we define a set of n plus 1 elements over here. These are 0 to n compositions of f on A. And there are n plus 1 because it goes from 0 to n. And by the pigeonhole principle, we say that there are two different elements of this set. So I've indexed this a bit weirdly, but I say there's two elements of this set, f to the I and f to the j, where these two elements are equal. Because by the pigeonhole principle, because n plus 1 is greater than n, there must be at least two elements which share the same element. Cool. And I've also said, for the sake of, without loss of generality, let's say I is less than j. We just want to know that I and j are different. And this is going to be useful because now we can say j minus I is greater than 0, right? And if we imagine f to the I being like I compositions of f, like this, right? And j being more compositions of f, right? So these are I compositions and these are j compositions. This thing here is composed more times than I. And what that means is we can take away some of those i's, as I've done over here. And now we're going to use the property of injectivity that Rashid covered, which is that, firstly, f to the I is also injective because a composition of injective functions is injective. And secondly, if we have f to the A equals f to the B for injective functions, then we can simply state A equals B. And so when we remove f to the I, we simply end up with this result, where k is equal to j minus I. And again, we note j minus I is a positive number. And we're done with the question. Again, line of reasoning is very similar to this diagrammatic approach we've done here. The only thing we've changed is this final step, where instead of trying to find some previous injectivity argument, we've simply used the property of injectivity, where we can remove this fi and this fi. Cool. Any questions? Nice. All right. Let's move on to another method. So that was pigeonhole principle and being cool with functions. We're going to talk about induction now. Oh, that was a bit of a spoiler. So we want to prove that for all integers n greater than or equal to 8, we can write this in terms of natural a and b. So this looks very similar to Bezout's identity. You might be thinking, can we use Euclidean algorithm? Because this is very general, like you can't use Euclidean algorithm infinitely. Maybe there's like some smart way to do it. It's a bit sketchy. One observation is that because that's a bit weird, you might notice, can we build up on previous solutions? And Yes, we can. If we add 2 to this equation, just as a simple observation, we can group up this 2 and 2a into 2 2a plus 1. So this goes here, and this is here and here. Okay, so why is this important? Well, this is important because if a is natural, then a plus 1 is natural. So this kind of begs like some nice way to construct n through induction. And I'm going to cheat a little bit. I'm going to cheat a little bit. I'm going to immediately just say we can write n like this for even integers. While doing this, you might notice that this sort of induction where you have to add 2, it works as a parity argument. So if I start with, say, like 8, and then add 2 to construct 10, and then add 2 to construct 12, I skip some. Specifically, I skip the odd integers. I skip 9, I skip 11, I skip 13. So we need, if we did this all by induction, we'd need 2 separate inductions. That's a bit annoying, so I'm immediately just going to note, I can write every even integer is 2 times something. You can do the construction as well for odd integers. It's actually not that bad, but just to showcase induction, let's use induction. So we start with the base case. We're going to use induction on odd integers, just going to clarify. Even inductions has a construction already. So for odd integers, we start with n equals 9. That's the first odd integer, greater than or equal to 8. And we can see 2 plus 7. I love math. And the second step of induction is to assume the hypothesis, inductive hypothesis. So assume this statement is true for some n equals k. So what we have, let's state our definitions correctly. We have k greater than or equal to 8, and we have natural AB. All those parts are very important. So we want to replicate the statement exactly as is. And the inductive step is to show this is true for k plus 2 as well. So using the observation again, earlier from here, we're going to replicate it as such. Noting that a plus 1 and 7b, a plus 1 and b are both natural numbers, we can write it exactly in this form. Over here, let's do some like matching. And we've shown that the statement is also true for n equals k plus 2. As such, over here. Cool. So the statement is true for all odd integers greater than or equal to 8. And since we've used a construction and we've shown a construction for even integers greater than or equal to 8, it must hold true for all integers greater than or equal to 8, because every integer is either odd or even. Cool. Any questions? Good. Nice. All right. Gardner University. I love it when a lecturer puts their name in a question. So we have a bunch of statements. Again, we've gone back to like logic now. Kind of funny. But this showcases a very interesting question technique, proof technique. So we have 41 students. We have a bunch of statements over here. And we want to show that at least one of them must be true. So there's a lot of combinations where at least one of them must be true. We could have one only true. We could have 1 and 4 true, and only those 2. We could have like a bunch of combinations. In fact, we'll have 2 to the 5 minus 1 combinations. Feel free to guess why. Yes. But there's a easier way to do this. If you have a question in the format of at least 1 or whatever, that sort of question, notice that it's excluding exactly one case. The case when all of them are false. Let's assume all arguments are false, right? For the sake of contradiction, what happens? Well, what happens is there will not be at least 3 out students. There will be 2 or less. There will be 9 or less business studies students, and so on. And we negate each of those statements, right? To sort of experiment and see what happens if this is not true. And we see that we have 40 students at most, because at most there are those many students for each of the subjects. But if there are at most 40 students, this contradicts there being 41 students, right? 41 is bigger than 40. That's not good. What went wrong? Our assumption. Our assumption was wrong. This is a proof by contradiction. So this must mean our assumption is wrong, and at least one of the statements is true. So to recap, we note crucially that there is an at least one condition, and so we are tempted to negate it and do a proof by contradiction. Cool. Great. Nice. All right, cool. I'm going to move on. And we have a recurrence relation question. Hopefully time permits. Let's try and go through as much as we can. So we have this fictional person called Cappy. They are described here through this image. They have 5 straight blocks. These are 3x1 tiles. So you can imagine I can put squares here. And they also have these L-shaped tiles. Oh, okay, it's orange. Like that. So we want to tile a grid. And I'm going to show you what that grid looks like. But we have these tiles, they come in these colors. There's 5 straight tiles and 3 L tiles. There's an unlimited amount of each tile, but these are the different colors. So we can copy paste as many as we want. So there are 2 types of grids. We have a 3x2 grid, 2x3 grid, 2 rows, 3 columns, and we have a 2x3n-1 grid. So AN has 2 rows and a multiple of 3 columns, so like something like 3n columns, okay? And BN has 2 rows and 3n-1 columns, right? So something like this maybe. Wow, that was horrible. Like that. So that's 5. But this top left square here is removed. So we get this L shape. Here's an example of B2. And essentially, they're different. The tilings are different even when they're rotated. So you can see they're different according to the line separating here, but they're not different according to colors. So this is important. And now we want to find a closed form for the number of ways. At the end, there's a bunch of subparts. We want to find a closed form for the number of ways we can tile that AN tile. This AN grid where we have 2 rows and a multiple of 3 columns. Okay. We can kind of see we want to construct a recurrence relation. So first we want to find the initial values A0, A1, and B1. So starting with A0, this one's a bit of a trick question. I did the exam and I got it wrong. It's actually an empty grid because I'm going to do a big that. It's an empty grid because there are no columns. And so the number of ways to tile is actually 1. The reason why it's 1 is that there's only one way to tile, which is by putting nothing. But the act of putting nothing is one configuration of tiles. So keep that in mind. That's a very annoying trick. There's one configuration for A0. For A1, we got some guy looking like this, right? There's 2 types of ways we can tile. First, we can either put a straight tile, right? In which case we're forced to put another straight tile underneath. We can't put an L because it covers 2 rows. And if we put 2 straight tiles, there are 5 colors here, and there are 5 colors here. So multiplying them together gives us 25 ways of tiling with straight tiles. If we were to put 2 L tiles, there's actually 2 ways we can put the L tiles. One L could go something like this, right? It can either face up like this, or it can be upside down. So the leftmost L can be down, or it can be upside down. And what this means is that there's 2 ways of orienting the leftmost tile. The rightmost tile is forced into one configuration. And we have 3 colors for each. And this means that in total, we have 18 ways to tile with L tiles. 2 ways for either configuration, 3x3 for each color, for the colors. And so in total, adding 18 and 25 gives 43 ways to tile this entire thing. Cool. Hopefully that was clear. And then for B1, we get a 2x2 grid that's removed because 3 times 1 minus 1 is 2. So this is now removed, and you can see that we can only fit a single L tile, like such. There are 3 colors, B1 equals 3. Sick. So that was for finding P and Q of this sort of recurrence. Oh, sorry, this is just initial values. Okay, cool. Now we want to try and construct a recurrence relation. So now that we've found some initial values. Okay, let's go with this. First, we notice we want to first find the recurrence relation for AN. So the question uses AN and BN. This allows us to compose later, as we'll see. First, for the recurrence relation with AN, we want to find P and Q. So to do that, we're going to hope this works. And we're going to see that if the leftmost tile is a straight line, so let's assume I have some like grid of ANs, and I'm going to consider the leftmost like 2 by 3 part. If I put a straight tile at the very end, right, I'm forced to put a straight tile underneath it, okay? So this means that we've got something inductive or reducing going on. If I put a straight tile here, then I'm putting another straight tile here, and I have 25 ways of choosing this section, if I do that, okay? I have 25 ways of choosing this section, and this section here simply represents AN minus 1. It represents the grid of AN minus 1, because I've removed a 2 by 3 grid from the left side. You can try and imagine what happens, like if I have an AN minus 1 grid, like such, and then I try and put another 2 by 3 grid on the left, I will get an AN grid, okay? So if I tile the left part here, right, I can do 25 ways of tiling this left part times number of ways of tiling the AN minus 1 grid. So that's where this idea it comes from. And we'll see this with BN if you don't understand. So that's if we use 2 straight tiles. If we use an L tile on the very leftmost, right? If we use a leftmost tile as that, right? It's not as simple, but we actually notice that if we remove this L tile from the rest of the AN tile, we get a BN tile. So this is crucial to observe because this entire thing here is 3n, and this remaining part here is going to be 3n minus 1 with a corner removed, which is exactly what bn is. So again, there are 2 orientations for the L tile, right? So how many ways can we put the leftmost L tile? 2 orientations, 3 colors, right? So 6 ways of orienting that tile, and the bn tile can be flipped the right way, or it can be flipped upside down, right? So this gives us 6 bn tilings in total. Okay, nice. Then we want to look for R and S. So this was the recurrence for AN. Now we want to look at the recurrence for BN. So notice that the leftmost tile for BN, right, it has to be wedged into this little space here, okay? So we actually have less options. If we put a straight tile on the leftmost tile, right, we're going to go case by case again. If we put a straight tile, okay, notice that to fill this section over here, fill the top section over here, we can't put an L because this entire thing is covered. We can't, oh, let's do that again. This entire section here is covered. This entire section here is covered. And we can't put an L tile like this, right? We can only put a straight tile, okay? So if we put 2 straight tiles like this, right, Bn gets turned into Bn minus 1, okay? Because that's what we're left with. If we remove 3 here, then from like 3n minus 1 minus 3 is equal to 3n minus 1 minus 1. Cool. So there are 5 ways of choosing the bottom tile and 5 ways of choosing the top tile. So we get 25 tilings for that, and Bn minus 1 ways to tile the rest of the space, as we discussed. Right? This remaining space here is Bn minus 1. So we have 25 times Bn minus 1 tilings. Then we have, if the leftmost tile is instead an L, so instead if we wedge L into the space, right, we have 3 ways of wedging this L. And you can imagine that because this entire length here is 3n minus 1, that's interesting. Yeah, if we imagine the rest of it is 3n minus 1, if I do 3n minus 1 minus 2, that's equal to 3n minus 3, which is 3n minus 1. So actually the rest of this grid here is going to be an minus 1. It's going to be the an minus 1 grid. Okay, so we're considering case by case, and we either get an an grid, or an bn grid, or an an minus 1 grid. Cool. Feel free to go over these notes again or ask questions in chat if you don't understand where all of that came from. So again, 3 colors for this tile over here, and an minus 1 ways to tile the rest of this. So you get another recurrence relation, right, with 3an minus 1, bn minus 1, and therefore we can write these 2 recurrence relations as such, where we consider the number of ways we can put the leftmost tile. And we get these numbers over here, answer the question. Cool. Nice. Yep. 25, sure. So for 25 for, let's say, an, right? So for the an recurrence, let's say I have this as my left part, right? And I have some more stuff here. Do you recognize that this remaining part is the an minus 1 grid? Okay, cool. The 25 simply comes from, I put a straight tile here and a straight tile here. How many ways are there? How many colors are there for the bottom tile? There's 5 colors, right? How many colors are there for here? 5 colors. 5 colors for the 2 straight tiles, right? So 5 times 5, 25. So 25 ways of configuring these 2. And then I multiply by an minus 1 to find the number of ways of configuring the rest. Cool. And a similar format for the bn thing. 25, 25, bn minus 1. Okay. Any other questions? All right. Nice. So now we want to find a recurrence relation that that relates only to terms an. This is a bit tricky because we have bn and an in our recurrences. So the trick is, first, we write our recurrence. We write this one here. We observe this recurrence relation has 2 an terms. This is going to be useful because if we write bn in terms of only an, we can hopefully substitute it into this recurrence. Okay, that's our goal, and it'll work because we're smart. And we get this recurrence here. If we do some rearranging, so we put 25 an minus 1 to the other side, so we get this one here, and then we get this guy here. So we have bn in terms of an with a bit of reindexing, right? Because we have a bn minus 1 here, we're going to aim to also substitute a bn minus 1 into that. Okay, so we have these 2 terms. They're all in terms of an, and that's useful because if we directly substitute bn and bn minus 1 here, we get this monstrosity, okay, which all simplifies down, right? If we multiply the entire equation through by 6, let me, this guy. If we multiply the entire equation by 6, we get rid of the 6 in each of the fractions here, and we get an 18 here. 3 times 6 is 18. And so these are our terms. Rearranging everything and grouping like terms, put a bracket there, gives us this recurrence relation. Hopefully the algebra wasn't too bad. It's just, again, we want everything in terms of an only, so we write bn in terms of an, reindex to get bn minus 1, and algebra multiplied through by 6 group terms. Cool. Makes sense? Any questions? Nice. And now we do the final part of this question, but we don't actually really do the final part of this question. We want to find the actual closed form for this recurrence. So this one is standard. If you know your recurrence relations, you first look at the characteristic polynomial of this entire thing. So what that is you look at the you look at the sort of characteristic polynomial as like, this is x squared, the an term is x squared, the an minus 1 term is x, the an minus 2 term is a constant, so 1, basically. And so if you rearrange that, you get x squared minus 68x minus 625, right, is equal to 0. So that's a characteristic polynomial. Yep. Yep, plus 625. Great point. And so this is a characteristic polynomial. Now you find the roots of this. Okay. You find the roots of this recurrence relation, and that'll be your K1 and K2. Okay. And after this, so after you get K1 and K2, you can then find A and B by using the initial conditions from earlier. So you substitute this with the initial conditions to find A and B, and you have the full recurrence relation. That's just more algebra. I won't go into it. Hopefully that's clear. Cool. Any questions? Any YouTube Live questions? Okay, cool. Thank you very much for coming. For the next revision seminar, we will cover combinatorics and graph theory. That will hopefully be awesome. Nice.
Next Thursday from 6 to 8 in Matthews Theatre C, if you're in person.
Nice. And thank you to the one person for coming.
Yeah.
Cool.